Ever since this LTZ 1000 moved in last year, I've been under constant pressure to do something with it. I don't want to be that one person who has everything but does nothing. In this video, I'm going to cope with my small budget and see if I can penny pinch my way to an LTZ 1000 reference board. Despite having South Indian blood, farming was never my strong point. This year's capacitors seem to have turned out fine though. Electrolytic capacitors are particularly sought after for their low leakage properties. Yes, you heard that right. As sketchy as the methods might seem, aging them artificially at a high current limited voltage reforms the aluminum oxide dielectric layer and reduces leakage current. Dramatic results of single digit nanoamps have been reported. Using the 10 input impedance of a DMM in series with the capacitor as a current shunt is more of a hack, but usable readings of small currents can be obtained. A couple of volts translates to several hundreds of nanoamps, which won't do. The fact that I'm using my function generator as an adjustable power supply speaks out about the pathetic power supply situation. Quick teaser, I think I have something to fix that on the way. All this fuss about capacitors is because I want the smallest DC voltage on the output of my high-pass RC filter, which filters out everything under 0.1 Hz. This RC filter with its unreasonable time constant is destined to be the front end of a low-noise amplifier. If I'm going to be working with an LTZ, currently or at least for a few more weeks the lowest noise voltage reference, I might as well make something that can measure noise, or at least zero point 0.1 to 10 Hz noise in general. As usual, I was unwilling to put in the effort to make an LNA from scratch, so I employed the help of a familiar product. The BioAmp EMG pill is basically a low noise amplifier, but it doesn't seem to be suited to the realm of 0 0.1 to 10 Hz. Shh! Don't tell the excellent people at Upside Down Labs lest you disturb them from their marketing trail. I was supremely confident in the simplicity of my design and hastily assembled a prototype. There's two caps on the input filter since I couldn't really find one with low enough leakage, and I had the bright idea of cascading two filters which dramatically reduces the voltage across the second and hopefully leakage. The main source of my confidence is this OP27 from the Marco Reps collection with a minuscule input noise of 80 nanovolts peak to peak. There's an old saying that says oscillators don't and amplifiers do, and this amplifier really does. More worryingly, the output slamming between the supply rails is causing my only specimen of OP27 to heat up, but luckily it escaped unharmed. Back to the bench. I got so desperate that I started trying to figure out how JFETs work so I could make a discrete amplifier. But luckily I didn't have to because this design from FESZ Electronics, link in the description, worked. And gave me some confidence to try my own design. And finally, after many hours and a gain of 10,000, I can see a 1 microvolt peak-to-peak sine wave with my own eyes. In the end, I ended up using an inverting configuration. The RC filter limits the lower end of the frequency range to around 0.1 Hz, and the 120 nanofarad capacitors across the gain setting resistors set the upper limit to around 10 Hz. And on connecting the input to a voltage source, the familiar roller coaster of 0.1 Hz to 10 Hz noise appears. Meaning this project worked and I was able to get away with using mostly dirt cheap parts and setting a positive outlook for this low budget journey. The custom made case left something to be desired, but the board fits inside and the halves can at least be zip tied together. Sadly, the output noise is left untouched despite the shielding. A mild steel case would have disintegrated in the hot and humid South Indian climate, or so the maker of my case thought, before convincing me to use stainless steel. I have absolutely no idea what carburized is, but let's roll with it. Aviation style connectors seem to be all the rage with the mechanical keyboard community and form the input connector. Ironically, despite having come so far, I never ended up using my LNA to measure the noise of my LTZ. I'm hoping that some quantum mechanical paradox translates no measurement to no noise. This video was originally going to be sponsored by Lion Circuits, but I was broke enough to keep this video free for another sponsorship, but that didn't work out, so here's the actual unboxing of these LTZ boards. In retrospect, I could have done a better job with the layout. Thicker traces and planes, for instance. Real LTZ 1000s are hard to come by and very expensive, and risking my only sample to an untested PCB could only result in disaster given how my luck is going. This is the TOD 1000, a completely pin-compatible LTZ 1000 alternative, and it is at least 2 orders of magnitude cheaper. The best part of this is it actually works. although covering the simulated heater resistance in hot glue was not the best idea. With the reference figured out, the next set of parts are the key to an LTZ stability: hermetically sealed Vishay thin film resistors. These footprints on the PCBs were meant for them under the assumption that I would somehow be able to source some samples, but that was nothing more than a pipe dream. Marco reps showed up to rescue me once again and sent me some thin film resistor networks and an open challenge. Turns out these 8 resistor networks can be configured in various ways to simulate the Zener current setting resistor and the critical 13K 1K divider. Another Voltnut came up with optimum resistor network configurations for various voltages and resistance ratios. Link to this repo is in the description. Another bonus is that you can actually buy these networks for cheap. The challenge set the basic premise for this video: temperature sweep an unheated LTZ and find the mythical voltage plateau. Set the heater divider to that temperature point and rejoice in infinitesimal tempco. To test tempco, I need some kind of thermal chamber. My first attempt involved printing one out of PLA with the expectation that the double wall would be enough to keep the heat in. PLA has a melting point of 60 degrees Celsius, and if I had been able to take it up to 100, I would have had a sticky orange mess all over my precious precision parts. Moreover, cheap Peltier modules are rather delicate, and I ended up breaking one. Here's a quick tip from Giannis. There's copper pads bonded to the ceramic substrate on the insides. There's nothing stopping you from using this as an SMD perf board with the thermal advantage of a ceramic substrate. The journey to a working temperature chamber was long and hot. I ended up using my 3D printer's heated bed, a 2-layer acrylic case with alumina fiber insulation, and a fan to keep the temperature inside consistent. I put together an entire video which is on my second channel. This very low budget looking test setup is controlled by my shiny new Raspberry Pi 4B, which talks to the printer and my Keithley 2000 over serial and logs data into a CSV file containing temperature and measured voltage. The 10K network is going to be the first victim of the chamber. For the first few runs, I set the bed to the end temperature and logged everything in between, but this left something to be desired. I rewrote the code to include a 5-minute soak time at each temperature step. The change in resistance is calculated in parts per million of initial resistance, and the temperature coefficient seems well within specifications. The cheap fan didn't like the elevated temperatures and gave up not long after. Looks like one of the windings overheated and took the controller with it. Luckily, I had replacements handy from the time I broke the printer's fan. Now that I know the setup works, it's time for the LTZ's first power up. The output is closer than expected to 7 volts, and there's something about these random last few digits that doesn't feel good. Maybe sometime in the chamber will do some good. The unheated tempo of this LTZ is an impressive 20 ppm. Well, in my defense, this is my first time working with such small deviations and I have every right to be impressed. Not so impressive, however, is the absence of a plateau. Following some godly advice, I added a top resistor to the reference Zener, and this was enough to flip the tempo polarity. The massive step in the graph is probably because of bad soldering. This at least proves that with the right resistor, the temperature coefficient can be cancelled out to a large extent. Out of curiosity, I enabled the heater using a composite 13K 1K divider, and ironically, here's the plateau. I would have loved to spend more time on this and gather more data and possibly make improvements, but my time finally ran out. My name is NNNI, and over the last 6 months I've endeavored to leave behind a stunning legacy for all Indian electronics YouTubers. But now it's time for me to start the next phase of my life in Germany. I may be gone for a while, but NNNI will be back, bigger, stronger and smarter.